is just, well, they can be written as this. F negative 1x. X equals f of y. Or they can say a reflection in the line y equals x. All of those mean inverse. Because all an inverse does is the x's and y's swap. X becomes y. Y becomes x. And then we said that it reflects in the line y equals x. The y equals x line is the identity line. Let's see how that even can work. So say I have this. So I just made this graph up. The identity line is when y equals x. So the identity line goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2, correct? It goes through those points. It's a true statement. And people are really good with realizing 0, 0, 1, 1, 2, 2. This was actually well drawn. These would be in a straight line. But I use graph paper. So people are, pretend that's straight. People are really good at realizing that 1, 1 is the same. If I flop it, it's still 1, 1. Flop it, flip it, it's still 1, 1. If I have negative 1, and I flip it, it's negative 1, negative 1. It doesn't change. We agree? But what people forget about is that there are a whole lot. My phone's trying to help me. Let's see, is it, how can I help you? I don't want you to. Okay. So there are a whole lot of values that fall on that line as well that are itty-bitty little dots that fall between 0, 0, and 1, 1. We agree? Like if you look here, there are a whole bunch of points that lie right here, don't they? Like for example, 0.5 and 0.5, 0.1, 0.1, 0.1, 0.2, 0.2, 0.3, 0.3, 0.4, 0.4, correct? There's a whole bunch of decimals that land between 0 and 1, that land between 1 and 2, that land between 2 and 3 on that line, correct? So people will always tell me invariant points if it's like 4, 4. They're like, obviously, that's invariant. It's 4, 4. It's going to swap. It's going to stay the same, correct? But then they forget that there's actually a whole bunch of dots in between that it could also fall on, okay? Now, an example is I could give you a graph like this. Called the cubic function. We're going to be doing this. If I wanted to know how many invariant points there were on the inverse, I would just draw the line y equals x. We agree? Now, often people will only pick the ones like 0, 0, 1, 1, 2, 2. But remember, the line y equals x also covers all of the 0.1, 0.1, 0.2, 0.2, 0.25, 0.25, 0.75, 0.75, 0.66279, 0.66279, right? Like it covers all of those decimals. When you flip them, you get the same thing. So the best way to find out how many invariant points are on the inverse is to actually just draw this line and see how many times it crosses. Here's going to have the same x and y. Here's going to have the same x and y. And this is going to extend. So here's going to have the same x and y. So there would be 3 invariant points on that graph, correct? So if you just remember, the quickest way to check for invariance on an inverse is to just draw the line y equals x and count how many times it crosses. It's a really easy question. If you forget that, you're staring for life for a while and it gets really complicated and you try and find decimal and it's just a mess, right? But if you remember that y equals x contains all the same y's and x's, and I flip them, I'll get the same thing. It's very quick to find the invariant points. Now, if I want to find the inverse, I'm going to label this blue one as f of x. If I wanted to find the inverse of that graph, the mapping of an inverse, I'm going to use black. The mapping of an inverse is xy becomes yx. The great thing is the inverse is a standalone. It's a standalone lesson in transformations. Like, you know, stretches and reflections and translations all came together. We could throw them all together and you have to know all of them backwards and forwards together. We agree? Inverse is its own lesson. You either ask to find the inverse or nothing to do with the inverse. That's it. Okay? So it doesn't get compiled in with, and now I'm going to take the inverse and I'm going to stretch it this and translate it. It's not. It's a standalone. I either ask you to find the inverse of it or ask stuff about the inverse, right? That's it in this lesson. It doesn't go with the other 3 lessons that we did. All right. So if I want to find the inverse of the f of x graph, so say I want to find f negative 1x, which is just a fancy way of saying inverse of the f of x, I take the points. So this one here is at negative 4 and 4. And it's going to become what? 4 and negative 4. They just switch. The key to inverses is drawing your points sequentially, and when you get from one point to the next, connecting them. Because if not, you'll have like 4 dots and people connect them wrong. It's like the saddest thing ever. Like I can see they did it, and then they just forgot to connect the dots, and they guess which way they connect, and they get it wrong. So I'm going to move to my next one, which is beside it, because it connects to it. So this one is at negative 1, 0. It's going to be at 0 and negative 1. I plot it. I connect it. Then I go to my next one, which is 1, 0. It's going to be 0, 1. Plot it, connect it. And then I go to my last one, which is 4, negative 3. It's going to be at negative 3 and 4. Plot it, connect it. So it actually reflects it in the identity line. And if this was drawn to scale and properly, it would look more, which it will down here. Where's the only place it intersected? The 2 graphs intersected, which I should label as f negative 1. Right here. What's that on? The y equals x line, the identity line, right? So we have one invariant point. So do you have to actually sketch the other graph to get the invariant point? No. Keep your phones out, make sure they're away. All right. So here we have the graph of f of x is x minus 5 squared. I want you guys to draw it down here. This one, x minus 5 squared. I'm not going to tell you how. I want you to see if you can sketch it somehow, however your brain does it. Sketch x minus 5 squared on here, and then I'll show you how I would do it. If this was Crystal in high school, I would type that into my calculator and just plot off the tables. I find my minimum, and then I find my plots off tables. If this is Crystal as a teacher, I now do everything through transformations if I can. So what could I do? I know that this is moving the x squared graph 5 to the what? 5 to the right. X squared graph is at 0, 0, so now it's going to be at 1, 2, 3, 4, 5, 0. Then I have negative 1, 1, so it's going to be negative 4, 1, or 4, negative 4 and 1. Oh my goodness. 1, 1 is now going to be 6, 1. And then I have 2, 4 is now going to be negative 2, 4, sorry, is now going to be negative 3 and 4. Struggling. And the way you could move it, which this would have been easier if I would just done this, is you could actually sketch the parent function of y equals x squared, right? And then I just moved it all 5 to the right, correct? You wouldn't have to do that. I'm just showing you how I would do it now. In school, I would have typed that sucker into my y equals as quick as possible, and I would have went to the table of values and would have pulled the points off. But now you know transformations and you forget you do. But last year, when we did quadratics, it was a time to discuss transformations because you guys would always put it into vertex form, and the moment you had it in vertex form, you actually had it in transformed form. Because in vertex form, you have your A, your P, and your Q. Your A is your vertical stretch, your P is how you move horizontally, and your Q is how you move vertically. So actually, last year, you were ready for transforming. Okay? So I'm going to label this black graph f of x. We always need to label, always, but especially when we have more than one graph. Now, I want to just graph the inverse. Just graph it. How do I change it? How do I graph it from f of x? All my x's become y's, and all my y's become x's, because my mapping is xy becomes yx. So my first point is at 3 and 4. It's now going to be at 4 and 3. So I go to 4, 1, 2, 3, 4, and 3, and I plot a dot. Now wait a second, does that make sense? Let's put the identity line on here. The y equals x line. Pretend that's perfectly straight. I was just looking at this black dot, and now I just drew this blue dot. Are they mirrored in that red line? Yep. Sometimes it's hard to look at it like this, so if you flip it so that this is actually flat, horizontal, because you can turn your page, right? You can take it out of your book. You can turn your page, you'll see that they're actually one on top of the other, right? So, looking good, it's looking good. Let's go do more. So now we have 4, 1. It's going to become 1, 4. And I do it sequentially because I'm going to plot 1, 4 now. 1, 2, 3, 4. And I'm going to connect it. Now look, this is just like, it's just a line between the two, right? But I'm doing this line right here. Then I have 1, 2, 3, 4, 5, 0. It's going to become 0, 5. And that is where it's connecting. I know this came out with an arrow. Then I have 6, 1. It's going to become 1, 6. And then I have 7, 4. 2, 3, 4, 7. Now, if I actually extended the blue out, I extended the black up. They're going to cross here. Use yellow. They intersect here, and they intersect here, which are both on the identity line, correct? And then I have to label the blue F negative 1x. So here's the yellow. I marked the invariant points on the grid. So we can do all of that without an equation. We agree? All right. But let's go up here. Because up here it actually says write the equation of F negative 1x. What is invariant, or not invariance, inverses? Inverses are what and what switch? X and Y switch. So in an equation, what's going to happen? X and Y are going to switch. That's going to be the very first step. Most people get stuck and don't know where to go. So the first is, this is f of x equals x minus 5 squared. Well, our first step is going to be to write x instead of f of x, because f of x is just y, equals y minus 5 squared. And that technically is the inverse equation. However, they're 99.9% of the time going to want it in y equals. So we're not actually done. But that is an inverse equation. It's just not going to match any of the multiple choice to the numeric response order that they want. So how do I get y by itself? How do I get rid of the squared? Square root it. And when you take the square root of anything, what do you have to remember to do? What has to go in front of the square root sign? plus or minus. So if there was a square root, like y equals square root, if say they gave you this, right? That's just positive. We agree? Because they gave it to you that way. So you can't be like, oh, they forgot the plus or minus sign. Silly people. You can't add more on. But when you're physically taking the square root of something, you must always put positive or negative because you're going to get two options. So the square root and the squared cancel. And I'm left with plus or minus root x equals y minus 5. And then I just have to add 5 to both sides. So I'm going to get y equals 5 plus or minus root x. You could write plus or minus root x plus 5. It just looks funky. So you just put the 5 first. And they wanted the equation f negative 1x, right? So now I have to write f negative 1x, the inverse of f is 5 plus or minus root x. There is no plus or minus button on your calculator. So what you would have to do is actually type it in separately. So go into your y1 and type in 5 plus root x, and then go into your y2 and type in 5 minus root x. So your y1 you have 5 plus root x, and your y2 you have 5 minus root x. Now put into your y3 the original, bracket x minus 5 squared. Put that into your y3. Can you find the invariant points? How do you find them? Second, trace. That's where we always go to calculate things. What are we going to look for between the two graphs? Where they intersect, number 5. And then you're going to go enter, enter, enter. So if they ask for you to find the invariance algebraically, you can't do it this way. But if it's a multiple choice or something like that, you can absolutely use your calculator. So what's one of your invariant points? There's 2 of them, correct? So if you want to go find the second one now, you have to go second, trace, intersect again. And you have to move your cursor to the other intersection. If you don't move your cursor, you're just going to consistently find the exact same intersection point each time. So you have to go second, trace 5, and then move it to the other graph. Enter, enter, enter. Did you find both of them? Did everyone find them both? You have to have 3 equations in your y equals, right? You have to have the 5 plus root x, 5 minus root x, and the x minus 5 squared. And then you go second trace 5, math enter, enter to get this one. And then you have to go second trace 5 and arrow yourself closer to this one. Move the cursor over here blinking and then go enter, enter, enter. Right? You have to move it. This is the fun thing. There are 4 intersections, but only 2 land on the line y equals x. We agree? Okay, go to your y3 and take that one out. Take out your original. Now in your y3, put y equals x. Put the identity line. Because really that's all we care about, where it intersects with the identity line. So we can use the inverse graph and the identity line, or the original and the identity line, and find out where they intersect, right? So now go second trace 5, enter, enter, enter. And then do it again, second trace 5, move to the other one, enter, enter, enter. So do we actually have to have both equations to find the invariance? Do we have to have the original and the inverse to find the invariance? Nope. You need to have the original or the inverse and the line y equals x on your calculator. We agree? So as long as you have y equals x, you could do the original and find the intersections. You'll get the same answers. Because it's where it intersects with the identity line, this y equals x line. Does that make sense? So how does the graph of f negative 1x compare with the graph of y equals f of x? They're inverse graphs. And they're a reflection in the line y equals x. So anything that lands on the line y equals x will stay the same. This one's f of x. They want you to sketch the inverse. Try it out. I want you to sketch the inverse and label the invariant points. Okay, I'm going to use this point, and this one. We'll say. I'm going to guesstimate them. So this one is at negative 3, 1. It's going to become 1 and negative 3. And then this one is at negative 1 and 4. It's going to be at 4 and negative 1. And then this one is at 1, 0. It's going to be at 0, 1. Now the identity line, or the line y equals x, which it reflects in, is right here. And where do they intersect? On it. So you don't actually have to find the new graph to find the invariant point, right? You could just take the original intersecting with the line y equals x and find the invariant point. You wouldn't even need the new one. Okay. We're going to look at this one. We're going to example 4. So we have y equals square root x minus 2. Now some people might say, it's missing the plus or minus sign. It's not. They drew it. You can't just add it because you feel like it. You can't be like, sir, you didn't. Also, if you did put the plus or minus, it's not a function. Remember, functions pass a vertical line test. If you put a plus or minus on a radical, it'll actually give you both arms. And does that pass the vertical line test? No. For every x, there'd actually be 2 y's, and for a function, we can only have 1 y. That's why they can only either put the minus sign in front of the square root or the plus sign in front of it if they're saying it's a function. Okay? In this case, they're saying it's a function, and it's been moved 2 to the right. Your radical graph, don't do this, you're going to type in your calculator anyways, but I just want to show you. A radical graph is normally 0, 0, 1, 1. We've talked about this before, 4, 2, and then 5, 6, 7, 8, 9, 3. We agree? That's your normal base function for y equals root x. You're not drawing this, we're just using your transformations to prove it. So I don't need to go to my calculator anymore to draw this, because I have that one memorized, but also you could do a table of values quite quickly, because your y's are just the square root of your x's. Now, y equals square root x minus 2 is just that parent function moved 2 to the what? 2 to the right. So this is going to be here, this is going to be here, this is going to be 2 to the right, this is 2 to the right, so technically be off the page. And that would be my actual function I wanted to draw. Now, could you just type it into your calculator and pull it off the table of values? Yep. But I wanted to prove that if you know the parent function of a whole bunch of functions, you don't actually need your calculator anymore. You just need to know transformations and what all the parent functions look like, right? So, we have this green graph because we drew the red one and then moved it, right? This is where we're sitting. Now, they want us to sketch x equals f of y. Now, watch this. If we actually do the equation of it, we're going to go x equals square root y minus 2. We agree? If we're trying to find x equals f of y, that's just a fancy way of them telling you to find the inverse. So they're telling you to swap the x's and y's. What do I have to do first here? Square it. So I'm going to get x squared equals y minus 2. Then what do I have to do? Add 2. So I get y equals x squared plus 2, which is just the parent function of x squared moved 2. Where are we moving the 2? Up. Moving 2. Up. Right? So our x squared is normally at 0, 0, 1, 1, 1, negative 1, 1, 2, 4, and then negative 2, 4. We're just moving it 2 up. So instead of being 0, 0, it's going to be here. And then 1, 1 is now going to be 1, 3. Negative 1, 1, negative 1, 3. 2, 4 is now going to be 2, 6. Negative 2, 6. Wait a second. Wait a darn second. There are 2 arms on that sucker, and there is 1 on the other. What the heck is wrong with this graph? The original radical didn't have plus or minus, correct? So it had 1 arm. We agree? So we can say this is the inverse graph. However, which one of those arms are we actually keeping? The one on the right, correct? Because this one actually reflects this green graph, doesn't it? Like if I throw the identity line up here. I'm keeping this graph, and I'm keeping this arm. I can't just say I'm keeping that arm. Like, you can't write and be like, keeping the right arm. Like, you can't do that in math. You have to restrict that graph. So if I just write this, if I write y equals x squared plus 2, I get this whole blue graph. We agree? But I only want the right one. I only want the red piece on that graph. So I have to restrict that graph's domain. What part of the x's am I keeping? Greater than or equal to 0. So I write this equation. I go y equals x squared plus 2. I do that, but I say x has to be greater than or equal to 0. And then it kicks off the other part of the graph. Because then I know, hey, actually this doesn't exist. Goodbye. And now do I actually have inverse graphs of each other? Yeah. So it's good to sketch it to see that you have too much. And then be like, oh wait, right, I need to restrict the domain. This happens when it's radicals, because radicals are the ones where you get plus or minuses, right? And in order for the original to be a function, you either have to do the plus or the minus. Okay. We're moving to the next page. I don't have that. Okay. So that's good. This is an outcome. I could literally list the outcomes for you that are in your curriculum, just in case you were curious. They're etched in my brain. Childhood memories out, Math 30-1 curriculum in. Like, did I go to school? Was I even in play school at some point? Did I go to kindergarten? I don't even know. But I do know that in the Math 30-1 curriculum, it does state that you guys have to do inverse graphs, inverse equations, state the invariant points of an inverse. But what you also have to do is restrict the domain of the original so that the inverse is a function. What the heck does that mean? That means if you have the original and it's a nice fancy graph, it's beautiful. Let's say it's a quadratic. Okay, pretty. If I go to draw it, it's going to be drawn sideways like this. It's not going to be a function. We agree? So what they want is, if they give you something basically with 2 arms, do you see how 2 arms is a problem? Because if you have 2 arms going like this sideways, 2 arms going like this sideways, a straight line crosses through 2 spots, we got issues, right? So an absolute value graph is a V. We did that last year too. Absolute value graphs are V's. Well, a V would be sideways with 2 arms. Would still be an issue, correct? So whenever you have that kind of graph, when you draw it sideways, its inverse graph isn't going to be a function. So what they make us do and teach you guys to do is restrict the domain of this graph so that when I draw it here, it has one arm or the other arm so that it's a function. We agree? So let's look at this one first. It's x squared plus 1. This is just the x squared graph moved 1 up, right? I'm going to go draw it. So 0, 0 is now going to be 0, 1, 1, 1 is now going to be 1, 2. Negative 1, 2, 1 is going to be negative 1, 2. 2, 4 is 2, 5. Negative 2, 5. It's a pretty graph. It really is. We're going to label it f of x. Very nice graph. Looks pretty. Great. I also know that when I turn it sideways, it's not going to be a function because it has two arms. We've discussed this already, right? So here it says they want the equation of the reflection in the line y equals x. They want the equation of the reflection. They just want the inverse equation. When I say inverse equation, you should say swap x, y's. When I say inverse equation, your brain should say swap x, y's. Like that should be the very first thing, right? Because if you can swap x, y's, most people realize after that they have to get y by itself. It's the whole, like, they'll just stare at it and be like, I don't even know what to do. If you're at that point, that's a scary point. So when you have to find the inverse, you swap x, y's. Swap x, y's, swap x, y's. Okay? So that's what we're going to do. We're going to go x equals y squared plus 1. And like I said, if you get the first step, swapping x, y's down, most people know then to get y by itself. Okay? But it's that first step that people either get or don't get. So I either have questions completely blank or perfectly done. There's no in between. Okay? So, how do we get y by itself? Do we take the square root first or subtract the 1? Subtract the 1 because when you're isolating, you do reverse bedmass. So we have to get rid of all the additions and subtractions first. So we go x minus 1 equals y squared. And then I'm going to square root. And when I take the square root, I have to what? Positive or negative. And then I'm like, uh-oh, because I know that positive negative of square root gets me a not a function, actually, right? It's going to get me two arms sideways, and if I draw a vertical line through it, it ain't passing. We agree? Okay, let's solve the conundrum. Here is my graph. It's in my hands. I feel like I got the whole world in my hands. Should be a world in here. I would be great picture. Okay. This is good. Lovely. Great. Inverse. This is good. Lovely. Great. Inverse. It doesn't work. It's like, it does. So, if I went like this, poof, it would be pretty, right? If I went like this, it'd be good, wouldn't it? Only problem is this goes to bad, right? So, what do I need to get rid of to make life good? Make the inverse be a function, technically. Get rid of an arm. Like, toss that one off, or throw that one away. We agree? How do I get rid of this? How do I get this to say, go away, little arm? Like, remember, I can't write that. I get rid of the left one. I get rid of the right one. Like, you can't write that. How do you mathematically tell people to, like, get lost arm? Mathematically. How do you tell this arm to get going? Restrict that domain, right? So it really depends on where the heck the domain restriction happens. In this case, where is the middle of my graph happening? What x is the middle of my graph happening? The vertex on. It's on 0. So if I kibosh this one and say, hey, I only want where x is greater than 0. I got this one, right? Or I could be a rebel and be like, we've done that already. No, thank you. And then you say, I actually want to keep when x is less than 0. Poof. This one's gone. Still going to work, isn't it? Yeah? So you just need to restrict the domain of the graph so that when you draw the new one, it's a function. We agree? So here it says, we're going to go right to here. Describe how the domain of f of x could be restricted. And we always restrict the original. On the test, half people will restrict the range. They'll be like, I'll just restrict it now. You can't restrict it now. You can't restrict it once you've got the inverse. You have to restrict the original so that when you do the inverse, poof, no problems are there. Okay? So I'm restricting the original, always, original. So in this case, I would say, okay, I'm going to use the equation f of x equals x squared plus 1, because I like it. It's nice. It was also given to me, so I have to use it. It's kind of forced. I have to restrict this domain so that when I go to draw the new one, life is good. We agree? So because we did greater than or equal to 0 last time, I'm going to be a rebel. I'm going to say I'm going to keep x is less than or equal to 0. Right? So if I wanted to restrict the domain, I would say, squiggly bracket, x such that x is less than or equal to 0, x is an element of the reals. And you have to do it in this format. Why? Because it all means something in math. Math has its own language. We know that, right? So the squiggly brackets mean the set of x values, because my variable for x is x. If my variable for x was m, I'd put an m there, just so you know. And then this up and down line means such that, and it will be in proofs in university if you ever take math proofs, math disapproof, such that x is less than or equal to 0. And then I do like a little like, and by the way, of these x less than or equal to 0s, I'll accept all the real numbers. So what does that mean? That means I accept every single little dot and decimal that exists from less than or equal to 0, correct? If I said x is an element of the integers, that would mean that I would accept everything less than or equal to 0 and just the integers. So like if I went to draw this graph, don't do this, it's wrong. If I went to draw this graph, all I would have is this. If I had x as an element in the integers, because then that would mean I would only be able to keep x values that are integers, correct? But I say x is an element of the real number, so I'm like, yes, all of these. Poof, there it is. Okay? So when you go to restrict the domain on a test, when it asks you to draw the graph with a restricted domain, you only draw that arm. Do you agree? Then people are like, oh no, I don't know what graph. So then they'll draw like 1/2 of the other arm. Why are you doing that at all? You should be drawing your graph off of your restricted graph, correct? Because all I do is I take my x's and y's and flip them, redraw, done, right? Don't overthink the situation. So what do I have? I have 0, 1, I now have 1, 0. Okay? I have -1, 2, I now have 2 and -1 with a little curve. Then here I have -2 and 1, 2, 3, 4, 5. Now I have 5, 1, 2, 3, 4, 5, and -2. Boom, I drew the restricted one. And how do I know, how do I feel good about myself? Because I say, oh, there's an identity line in here. There's the line y equals x. I'm just going to sketch it quickly. Does it look like it's mirroring on it? Yep. So I feel good. Okay, I'm going to give you a different one. You can do it in this space down here because I'm not going to do this. I'm going to give you this. Y equals the absolute value of x minus 3 plus 6. And I want you to restrict the domain so that the inverse is a function. If you want to graph it on your calculator, I'll remind you where the absolute value function is. So you go y equals, and then you press math, and then it's the apps. Over to none. So if you want these little lines, you're going to go to the y equals, and then you're going to go math and over to num, and it's number 1. Or you can remember that the parent function of y equals x is that y equals every absolute value x. So it actually looks like this. My x's all become positive, so it's just 0, 0, 1, 1, -1, 1, 2, 2, -2, 2, 3, 3, -3, 3. And I'm just taking this graph and doing what with it? Moving it 3 to the right and 6 up. What part do I actually only care about that if I'm restricting the domain? It's 3 to the right. Try it out. Restrict the domain of this one so that the inverse is a function. So this is moves 3 to the right and 6 up, correct? So like your original vertex is going to be like here and then here. And then it's going to go like this. Do you agree? Quick sketch. So what part am I cutting off? Either this arm or this arm, correct? So we went over the domain that we can restrict that would leave us with the most graph that would still be a function, correct? Because if I cut off the last one at 0, I was left with either this full arm or this full arm. So that was the most amount of graph that I could draw that would still, my inverse would still be a function, correct? So what's the domain I could restrict here? I could go x such that x is what? My split would be at the 3, right? So I could say either x is greater than or equal to 3, xer, and that would get me the right arm. Or I could say x such that x is less than or equal to 3, xer. The problem with these is that I'll have people draw the graph to the restricted domain of the less than or equal to 3, and then they'll say, I restrict the domain to greater than or equal to 3. Like, you'll restrict the domain to the wrong graph. So, like, if you're picking x is greater than or equal to 3, you have to draw this arm here, right? If you pick less than or equal to 3, you have to draw this arm here. Because, like, alone, this arm by itself is good. This arm by itself is good. But if your domain restricted to the wrong arm you drew, that's, I have to pick one of them to be right and the other one to be wrong, because they don't coincide, right? You have to pick that on your day. Now, that gives me the largest amount of graph that I can draw for it to be a function. But could they actually give you different domains that aren't just 3's? So here's my cutoff of 3. What other thing could I say x is greater than or equal to that would give me a domain that would work? What if I used 4? If I used 4, 4 would be here. Oh, good, I picked it up in the blue side. 4 would be here, which would give me this arm. Would that still work? Yeah. Would it be the most amount of graph? No. But could it still work? Yeah. So they could give you that as a domain on a multiple choice. It might not even be the 3. They might say x such that x is greater than or equal to, and they could go 5, they could go 6, they could go 4.5, they could go 9, because anything greater than 3, they'll just cut less of your graph off, but it still would work, right? You'd still end up with that arm. So I could say 7, and this would still be true. For less thans, instead of using 3, what would I have to use? 2, 1, -7, -100. It would be really weird and down the side to graph it, but it would still work, right? So you could go like -5, because -5 would be like here and then that way, which is still only an arm. And if I drew that, it would still work. Do we agree? So don't get just locked on the 3. Now, if you're allowed to pick it, I go to the vertex and I go less than it or greater than it. I do that every single time. But I don't want you to be, and I used to just teach it only that way because it's easier. However, what happens if you get a multiple choice and they give you x is less than or equal to -5 and 3 is nowhere to be found on it, and then you're like, Lepp, you destroyed us for life. Like, there's no 3 and this is what you taught us and now we can go no further. I cannot expand on what you've taught me. You taught me 3. So, heaven forbid that happens. I do not want you to be hammed in by the 3. Okay? So do you understand how it could be something greater than 3? You just have to pick a number greater than 3 or less than 3. Okay? Biggest error happens in here. This is what happens. I will give this. Okay? If I do this, bad things happen. So I do it to see what happens. Because I'm mean like that. So say I give you this graph. Okay? Do you know how many people will tell me, and this is the number 4. So you know how many people will tell me, okay, I'm restricting it to x such that x is less than or equal to 4, xer? Because they're pulled to the number. Is that anything to do with an x? No. What is the x being cut here? 0. This should be a 0. So some people luck out because they'll say x such that x is less than or equal, or they'll say x is greater than or equal to 4, which actually just works out because x is greater than or equal to 4 is greater than or equal to 0, and they luck out. but I know what they did on that test, and I'm like, you just lucked out because your reasoning was bad, you know? So watch yourself when it is hammed onto the y-axis. I know that some people will pull themselves to the actual y value, not the x, because the x doesn't scream, it's a 0, but the 4 screams, I am here, you know? If I do it over here, though, and this is -6, people will do this one better. It's just the one that's on the y-axis. It's just how it works. So watch yourself. It's on the y-axis. It's greater than or equal to 0 or less than or equal to 0. Okay? You have a little bit of homework. This is the last lesson of transformation. We've just finished 2 units. Just looking up. We're still on the way up the hill. I picked all because it has 4 graphs and they make you restrict the domain so that the inverse is a function. And they drew the graph, so it's not like it's a hard one to do, but it's just solidifying more like, can you do it? So I try and max out on 8 to 10 questions. That's 8 total.